nanohub.org.
Online simulation and more for nanotechnology.
Okay guys, let's get started. We are going to start a new topic, and it's basically one of the most basic topics that I want to cover, one of the most important topics, model calibration or inverse problems. I hope one of the things that I want to show you is that you pretty much, every single one of you that does either something that has to do with science or engineering has to solve an inverse problem or a model calibration problem. Okay, the mathematicians probably don't, but they just have to find proofs. But the rest of us have to do it on a daily basis. And it's good to know, I mean, you probably already do that in one way or another, in ad hoc ways, and we're going to see a few systematic ways of posing these problems. Okay, but seriously, we do it pretty much all the time. So I'll motivate inverse problems. I'll just show you 4 or 5 inverse problems. There are thousands of inverse problems, and they're all of the same form. Okay, so using these 4 or 5 examples of motivation, we're going to come up with a mathematical formulation of a generic inverse problem. But it's going to be so generic that for some cases, you're going to have to, do a little bit more work and specialize it a little bit more, okay? And I will highlight these keys. So it's going to be ridiculously generic, and we're going to first introduce methods that work for this class of ridiculously generic problems. And of course, this is not going to work on every single research problem you have. If you have too many parameters to estimate, it's not going to work. If the solvers are too expensive, it's not going to work. But it is a starting point. To solve the inverse problems that we're going to pose, we will have to solve an optimization problem, and to solve an optimization problem you use derivatives. Okay. So we're going to have to talk again about the method of adjoints for taking derivatives of your models, and hopefully I will now have the time to actually show you how to do that. And then we'll just demonstrate what we have learned with a simple inverse problem. And I will tell you the shortcomings of the formulation that we're going to come up with. So what we're going to come up with is called the classical formulation of inverse problems. And I will tell you right now that it doesn't really work unless you have found the perfect model and you have very, very little noise in your experimental measurements. Okay, so if you are very confident, so for example, if you are, dropping balls and measuring how much time it takes to fall on the ground, so you're pretty sure that Newton's laws apply, and you want to figure out the mass of the ball, yeah, it's going to work very well, okay? But if you are doing anything more complicated, perhaps, the Newton's laws do not apply in your case, or there is a constitutive relation that is missing, that you are guessing, right? Then you're going to have to think a little bit more. But anyway, so the first example I want to show you, and this is the example that we're actually going to solve, comes from chemistry, chemical engineering. So it's the problem of catalyzing NO3 to get N2, okay? Basically, this is real experimental data, and here's how it goes. You just put this in a box, like you put 500 grams, let's say, of NO3, and you let it react, and you measure the concentrations of these different chemicals at 30-minute intervals, okay, and you just see how they evolve over time. And we have hypothesized a model for how the one chemical converts to the other chemicals. And this model is a dynamical equation that has, let's say, requires the rate of with which one chemical converts to another chemical. So let's call So if you call this weight K1, K2, K3, K4, and K5, these are the parameters that we're looking for, the rate with which these chemicals converge one another. And if you notice here, we have introduced an unknown chemical X, because as it turns out, the mass, so the total mass of the things you measure is not conserved here, so there's some missing mass that must have become something else, and that something else we don't really know what it is, so we're going to call it X. Okay, and of course this is a model, it may be wrong. Okay, maybe there are two X's, an X1 and an X2, or 3. Okay, but the problem here is to use the time series data, concentrations of the different chemicals measured at different times, to figure out the kinetic reaction coefficients. Okay, which are some coefficients in a differential equation that we're going to see in detail later on. We're going to spend quite some time there. Okay, so that's the first inverse problem that we're going to look at. And you can call it an inverse problem because you want to go, your model takes you from the case to what you're supposed to measure. And we're interested in the inverse problem, which is we measure the concentrations and we're going to go back and figure out what the reaction coefficients are. So you could call it an inverse problem, or you can call it a model calibration problem. But it's really the same thing. Okay. Here's another example. So imagine that you have a lake, and I mean, it's a strange lake because there are no waves in this lake. But it's still a lake that just stands still, okay? Let's say it's a pool, okay? And somebody pees in the pool, and you measure the concentration. I mean, it's not really a lake, because in a lake you also have advection, okay? Here you just have diffusion. So somebody pees in the lake, and you measure the concentration of P on the four corners, okay? And you, based on this time series, you want to infer which this person is. Okay, let's say you have a lot of people in the pool. You want to figure out who that person is. That's also an inverse problem, right? So we have, the model is basically the diffusion equation, and you're looking for the source term, okay? There's a typo in the diffusion equation, but should be a square there, the Laplace operator, okay? But, so you're looking for the source term, basically, okay? So you have time series measurements of the concentration of P, let's say, at the four corners, and you want to go back and figure out the source term.
What's the data?
The data are concentration of whatever chemical you have at these four sensor locations. Okay, so you just have the time series U of T at that X, at that X, at that X, and that X.
But the figure is from
What was that?
the corner.
Yes. So your data are from the corners. You just measure it at the corners. You don't really see this picture, right? You just see that you have somebody tasting the water, let's say, at the corners. Okay. I went too far. Okay, so, but that's the idea. So you have a sensor at the corners. Yes.
What is the data, the blue line or the red dot?
Oh, the data is the red dot. The blue line is let's say the best fit that we have found if we actually solve the problem. Okay, so the data are the blue dots, and the red dots, and you have these red dots at four different time instances. You have them at the four different corners. Okay, S is the source term. So it's like a function that tells you where you dump the chemical. Okay, and there's a square there missing. So this is just a function of x, let's say x and y. Okay, and it is basically a function that looks like an exponential, like this, for example, x minus x naught squared plus y minus y naught squared divided by 2, let's say sigma t, where t is the time. And this basically just puts a drop of the chemical at the location x0, y0, and this is what you're looking for, the location x0, y0. Okay, but this is just another problem. That I'm going to give you a homework on this problem. Okay, that's the problem you're going to do on the homework. So this is another example of an inverse problem. You have, let's say, an oil reservoir, and you have, let's say you're operating the oil reservoir for like a year, and you have an injection well. It's in the second stage of production. You have an injection well here and a production well there. You're pumping water through this well, and the water pushes the oil out of the other well. Okay, and then what really happens depends on the permeability of the ground, of the morphology of the ground. What kind of rocks do you have? Okay, so for different types of rocks, you are going to get a different oil production history, if you like, right? So now in this problem, what you want to do is look at the oil production history, let's say for the past year, and update your state of knowledge about the permeability of the ground. So figure out how the rock looks like from what you have produced, because what you know is, the rate with which you're pumping water on this well. Perhaps you also know the pressure at this point. You know the rate with which you are taking oil out of the well, and also you know the pressure there. Okay? And from these basically measurements, as a time series over a year, you want to go back and figure out the ground permeability. And how does the ground permeability connect with what you measure here? You need to describe the two-phase flow inside the oil reservoir, oil basically competing with water for a place in the well. Okay, which is not really fluid dynamics, it's a simpler equation. But it's a simpler equation than Navier-Stokes, but it's still computationally expensive. By the way, these are all problems that we have solved in our papers at some point. So you can actually go back, you can actually go and find the references and look at the actual equations. So I'm not just making them up. This is another problem. It involves the calibration of the community land model. The community land model is basically a sub-model of the community Earth system model, which is supposed to simulate the whole Earth. So the community land model just simulates basically the land and the plants growing in the land, the forests, the prairies, the agricultural land, this kind of stuff. So the biomass that grows on the ground. This is what the community land model simulates. And there is a part of the community land model that simulates crops. Okay? And in particular, there is a sub-module of that simulates corn and soy. Okay, so we're in the Midwest. Okay? So we have a lot of data for corn and soy growth. So when I was at Argonne National Lab, one of the things that we had to do was to calibrate this model, like this sub part, basically the parameters of the community land model that have to do with the growth of soy and corn. And it may sound simple, but you cannot really calibrate this model ignoring everything else. You have to simulate pretty much what happens in the Midwest over the course of, like, let's say 5 or 10 years, and use the data you have to go back and figure out what the parameters are. So just to give you an idea of how much time it would take to calibrate this model, it would take about 2 weeks on a supercomputer. And it's a black box model. I don't really know what is inside. The manual for the code is like 1,000 pages. And of course, nobody wants to change anything on that code. And it is not one of the most difficult inverse problems that you can solve. And imagine that it's just a tiny part of the Earth system model, which is not very well calibrated, by the way. So the process of calibrating it is still ongoing. All right, so other examples of inverse problems? Yes?
Predict the carbon quantity or something.
So you want, here what you really want to do is simulate the whole Earth. To simulate the whole Earth, you need to simulate crops, okay? And to simulate crops, you need to know how corn and soy grow in an uncertain environment. And that model predicts exactly that. Okay, so the plants basically grab chemicals from the atmosphere and they put them in the ground. And then they grow and then they die, and so on. So the whole process is simulated through that model. And yes, you just have to, it has parameters, okay, that we don't know what they are. Anyway, so here's a bunch of other inverse problems that you may have heard of or not. Seismic inversion. So this goes as follows. You have data from past earthquakes. Basically, you have sensors measuring the acceleration of the ground at various points, let's say in California, and you have data for the past 40 years, and you want to use this data to characterize how the ground looks like. Okay, and this is very possible because where earthquakes are just sound waves moving through the ground, and you can write down, let's say, the sound equation and try to come up with velocity of sound at different spots in the ground that matches what you're measuring. Okay, another inverse problem is non-catastrophic fault detection from current measurements, for example. Okay, so you have like a machine component that may have a defect, like a crack. Okay, let's say it's made out of metal. So you pass current through it and you measure basically its electromagnetic response. All right, and if there is a defect, what should happen is that the electric conductivity should change wherever that defect is. So that defect should change what you would ideally measure if you didn't have the defect. So based on the sensor measurements, you want to go back and characterize the electrical conductivity, say, of that component, if it is a metal, and you will see the defect. Okay, but again, this is not only an inverse. It is an inverse problem because you want to do exactly that, but you also have the problem of where you put your sensors, right? And what exactly do you measure? Another problem, kidney stone detection with ultrasound. Again, you know, you're hitting with sound something, you're measuring the response, and if there is a defect, the velocity of sound should change at that defect. And you can use you try to use your measurements to invert, let's say, the acoustic equation for the velocity of sound and figure out, you know, the distribution of the velocity of sound, and then you will see the defect. And there is no end to what you can do with inverse problems like that. Okay. So as soon as you have a model that predicts something, you can pose an inverse problem and go back to something else. And this is most of the times, you know, where applications come from. You go back based on some measurement and you use your theory. All right. Now let's formulate these problems mathematically. Okay, in the simplest possible way that you should not really use unless your model is perfect or close to being perfect, and you don't really have any noise in your measurements. But it's still the simplest way to start. Some things that we're going to need. We're going to need the space of model parameters, or parameters of your model, which I'm going to call x. Okay, lowercase x will be the parameters themselves. Scripted x will be the set of parameters, okay? And of course, I'm assuming that we have d parameters. Now, the experimental measurements are going to be denoted by y, lowercase y, the space of possible y's, script y, and I'm assuming that you're measuring m things. Okay? So you measure a vector. Let's say the response of something at different times, etc., etc. Now you should think of your model as a function that takes a parameter and gives you a y. Okay?
Why does the model take the parameters?
The parameters are the input of your model. So your model...
Input of parameters.
Yes.
Parameters are inputs.
Yes. So your model, for example, let's say that you have Newton's equations. Okay? Mass times acceleration equals the sum of the forces.
Yes.
A mass is a parameter to Newton's equations. So whenever you solve Newton's equations, you need a mass. The mass is an input. It's one of the x's. Make sense? Alright, so all the things that you have in your model that you don't know, we call them x. Okay? And all the things that your model predicts and you can measure experimentally, we call them y. Okay? If you cannot measure something experimentally, we throw it away. Okay?
So here small x is a d-dimensional vector.
Yes, small x is a d-dimensional vector, small y is an m-dimensional vector. And it goes as follows, right? So somebody gives you all the parameters of the model, you evaluate your model, and that's your estimate for y, f of x. Okay? And now this evaluation, of course, it may be a little bit complicated, right? So somebody gives you, let's say, the permeability of the ground in a text file. You convert it in the right format. You generate a mesh on which you solve the two-phase immiscible flow equations using, let's say, finite volumes. And then you post-process the result to extract the pressure and the oil concentration and water concentration as a function of time at two well locations. And you don't really need it at all the times, you only need it at the times you measure, so you post-process that a little bit more, and that's f of x. Make sense? So f of x may hide something like, write this input file, submit a job to the supercomputer, get it back, post-process it, get whatever we measure out of that, return it back. Make sense? Okay, so all the details are hidden inside f. And the inverse problem is really this. I mean, this is a naive statement of the inverse problem. Find an x so that f of x is approximately equal to y. Okay? Of course, this doesn't make sense if y is very noisy. And we will change it a little bit. Okay? So let's make it turn it into a problem that we can actually solve. And this is the classic formulation of inverse problems. So f of x is approximately y is not a little bit, but very vague. So what we're going to do is we're going to define a loss metric. A loss metric is basically a function that tells us how much our prediction is off if we choose x. Right? So it tells you that if you choose x, this is what you predict, this is how it is compared to your actual experimental data. Okay, this is how much off you are. So you're going to have to quantify this. If you can't quantify this somehow, of course you can, I mean, there are many ways to do that. Okay, and it is a very subjective thing. Then the inverse problem can be posed mathematically as an optimization problem. And the problem becomes, find the x that minimizes your loss. Okay? So you minimize your loss over x.
So are we assuming our function is
here you are assuming that your model is correct. Yes. You don't worry about that at all. Okay? So your model is supposed to predict reality. You don't really have a way with a classical approach to account for the model discrepancy.
No, I mean, how do I come up with F? The form of F?
The form of F, you come up with it from physics. Alright, so what is it that you do? You study oil reservoirs? Well, you talk to a petroleum engineer. Do you study, I don't know, pee in pools? Talk to a chemist. So it depends on the context. F of X comes from science. Okay? So, the choice of the loss is completely up to you. Different losses will give different results, and their loss should really be tied to your decision-making process, right? What does it actually mean for your application to be wrong? Okay? But anyway, if you don't really want to worry about that, the most common choice for the loss function is the square loss, where you say, what I want to do is I want to minimize the square difference, let's say the square error, okay, between my prediction and the measurement. All right, so you say, this is my prediction, this is the measurement, take the L2 norm between the Euclidean norm between them. That's what I want to minimize. Okay, makes sense. Basically the same thing that we did in least squares. So then your problem becomes this. Right, so the inverse problem can be formulated like this. Minimize the square error between your prediction and the experimental data. Okay? Now, of course, this is a problem that we have seen before in the very first lectures. If f of x is a linear function of x, then this is the classic least squares problem, and you can just solve it with linear algebra. Okay, there exists an analytic solution if f of x is linear in x. If f of x is not linear in x, then you cannot, there's no analytic solution anymore. There's not even a unique solution. Okay, there's always a solution, but it doesn't have to be unique. It doesn't even have to be a good solution. Okay. But in that case, you would call this problem a generalized least squares problem. Okay, because it's a least squares problem, but it's not the one with a linear function, it's a generalized one. Okay? Has a lot of issues, but it's really, I mean, if you are quite sure about, if f of x, if you're sure about this, and this has a low noise, then it will probably work. Okay? This formulation will give you really a good x. So for example, Newton's laws, you're looking for the mass, you measure, I don't know, a time or something with very high accuracy, using a high-speed camera, you're gonna nail it. Okay? You don't even have to worry about that. Just minimize the square loss and it will work. Alright. So in general, the problem is like this. You have to minimize some loss function. Alright, so let's look at what kind of techniques you can use to minimize the loss function. Alright, so you need a nonlinear optimization algorithm to minimize the loss, a generic loss function, okay? And here are some of them. Gradient descent is the most basic. Conjugate gradients is like the next step from gradient descent. Newton-Raphson is super powerful, but it requires second derivatives, so it should be avoided. BFGS which is a bunch of names basically, which of course I don't remember, okay? But you can look it up. It's known as BFGS. It's basically a version of Newton-Raphson that doesn't require the second derivatives. It kind of estimates the Hessian matrix on the fly. So it should be preferred. I mean, if I had to choose one of them, I would choose this one. Okay? But you cannot really get away without at least giving the first derivatives of your model. Okay? Now there are some Python libraries that you can use for optimization. So as soon as your f of x is a Python function, then you can use one of these libraries. SciPy optimize minimize basically allows you to choose from a suite of algorithms, including gradient descent, conjugate gradient, BFGS, Newton-Raphson, and many more. And the only thing that you have to provide is a Python function that implements f of x. Okay. PyOPT is another choice, and there are a few more, but I think for this course we're just going to use this one, okay, because it is everywhere, it works everywhere, etc. All right, so SciPy optimize works with just f of x. It doesn't really need you to give it the derivative of f with respect to x, okay? And it will look as if it works, and it will work, but sometimes it will not work, okay? So you need to know what it does. So if you don't give it the gradient of the loss function, let's say, with respect to the parameters, then it will do this. It will estimate the derivatives numerically using finite differences. Right? So you would just say, okay, here I'm looking at the derivative at x. What I'm going to do is I'm going to basically use the definition of the derivative with the limits, but I will not really take the limit. I'll just take a small h. Okay? And substitute everywhere I need the derivatives, I will be doing that. And that will work. I mean, we have autocorrector here, right? So it's not really spicy, it's SciPy. So, so numerical derivatives are, if you have a model that has, let's say, 10 parameters that you want to estimate, and you want to take the numerical derivative, you need to do 11 evaluations. Okay? So if your model is very expensive, it's not going to work. If you have a high dimensional model, let's say you have 100 parameters, then you're going to have to do 101 evaluations for one iteration of the optimization algorithm. And it doesn't really scale. Okay? So this is one problem. The other problem is that it is inaccurate, because unless you choose these eights just right, it's not going to work. And unless you pay attention to scale your x's properly and your f's properly, the default choice of eights for SciPy may not work. But again, it's just easy. Okay? So you should really just try it. If your model, the evaluation of your model does not really just costs electricity, meaning running your computer, but not for ridiculous amounts of electricity, then you can just try it. And maybe it works, okay? But be prepared for failure, because it never really works the first time. Anyway, so let's do now, let's solve a specific example. Okay, so we're going to look at the catalytic conversion of nitrate to nitrogen. And this is a complex problem, complex process that is not really well understood. We have intermediate chemicals that we don't really know what they are. And we perform an experiment in which we measure the mass of the known products, the products that we can measure, every 30 minutes. Okay, so these are the measurements. These are actual measurements from this paper. And there's also a little bit of noise in the measurements, which we're going to ignore for this lecture. So this is the data. Right, so you see that the rows correspond to different time steps, starting from the initial concentration, which we assume it is exact because you just put in there 500 grams, let's say, of nitrate, and the column corresponds to the different products. Okay, and then initially you may be inclined to create a model out of these products. like a differential equation that describes how nitrate converts to everything else and everything else converts to everything else, okay? But you know from physics that mass is supposed to be conserved. So if you sum up the masses on its row, you should get 500, but you're always a little bit short of 500. You get less mass, okay? So this is like the total mass. Which means that there is one more product, at least one more product, that you don't really measure, okay? But you see that it gradually goes away, okay? Anyway, this is the model that Katsunaros proposed. And the model involves basically the conversion of nitrate to whatever the second thing is called, and so on and so forth, with these rates. Okay? And this is a differential equation. So let's write it down as a differential equation. And that's a differential equation. It looks like that. Right? So you have here the rate of change of nitrate. Nitrate converts. I mean, it just decreased with this amount. All right. And what happens to this amount? This amount becomes NO2. Okay. And then NO2 is decreased with this rate, and what happens to NO2? Well, some of it becomes X, some of it becomes NH3, some of it becomes N2O, ammonia, whatever that is, and so on and so forth. What is it? Whatever. I have written it down, right? But I'm not really. One of the reasons I went to math is this. It's too difficult. The names are just ridiculously difficult.
So here, are you assuming we have only one?
Yes. Well, I'm assuming that there is only one product that is not measured. Okay, but this is just an assumption that turns out to be pretty good, but there could be 2 or 3 or 4. Let's not argue about this assumption. Anyway, this is how the model looks like. So what we really want to do is use the experimental measurements, which are measurements of the concentration at different times, and come up with these coefficients. These 5 parameters of the model, okay? So now you may be inclined to directly define a loss function based on the solution of this differential equation, but, and you know, don't even, what engineers do most of the time is they just, you know, would know what the problem is, and then they try to just code it. This never works. Never. Okay? It would be only for very, very simple things that it works, or for things that you have already done in the past. Then it may work. But if it is a new problem, you should probably think about it a little bit. I mean, we're not talking about crazy math, but perhaps, you know, write down explicitly what you're planning to do before you code it. So I have now broken down this process in steps. Okay? First, you get rid of complex notation. Okay? This is a no-brainer. So nobody wants to carry this around. You don't want to code this with these names. There's no way you're going to do that. Okay? So you just give the concentrations different names. Let's call them Z1, Z2, Z3, Z6. Now I can pronounce them. Okay? At least. And I can also code them a little bit easier. All right. So when you do that, and then you look at the differential equation and you realize that there is really a matrix on the right-hand side that tells you how product 1 converts to a different product and how product 2 converts to a different product. And you say, okay, let me just write down that matrix as a matrix because it looks a little bit easier. So you see that product 1 decays with, reduces with this rate, and it becomes product 2, and then product 2 becomes product 3, and product 4, and product 5 with the rates that are written like there. Okay, so this is like a little bit of bookkeeping. So at the end of the day, your quantity of interest z is just a vector that is different at different times, and the differential equation is just a linear differential equation, and the parameters are just some parameters that specify the values of the matrix. Okay, so this is a little bit easier to think about than this. Okay, and it is a little bit more general in the sense that, you know, if you want to try a slightly different model, then all you have to do is change the form of that matrix, and you keep everything else the same. Yes?
Why did you have so many zeros just to have a square matrix?
Yes, because the differential equation is going to be z1, z6 equals this matrix times z1, z6, and most of the interactions are not occurring. So you have to put 0 for the rates. And you only put something non-zero for the things that do occur. Okay? Anyway, but the whole point here is to just simplify the notation. Okay, that's the whole point. Yes?
Just look at this thing is going to work only if I have a perfect f of x.
Yes. This is a pretty good f of x.
But earlier you said that you're not measuring something, that's why we don't have
Yeah.
mass. Doesn't that make the f of x a little bit not so good?
Well, your model, you don't have to, that's a very good question. I will defer to a future lecture. Seriously, because I'm going to talk about model selection in a lecture called model selection. On purpose. And I will briefly touch upon it next time. I will just tell you right now that this classical approach to inverse problems does not allow you to ask this question. This is it's as simple as that. So you have to trust your model. If your model is bad, you're going to get garbage. And well, it will be pretty. You can see if your model is good after you calibrate it. If you just use another set of experimental measurements that you haven't really used in your, I mean, if we calibrate this and then we discover what x is and we actually measure it and this thing predicts what we measure for x, then we have done a great job. But we're going to have to ask this question later. But anyway, the problem now, the differential equation, the model on the background became this. Right? So you have a differential equation with this initial condition, and you can think of the solution as a function of your parameters. So you see that the solution at a given time is a function of all the model parameters. Okay? In that sense, the parameters are an input. Okay, but we're not done yet. We need to make the connection. Well, okay, before we make the connection between the model prediction and what we measure, let's scale the parameters a little bit, okay? Because these Ks, they have units of inverse time. We don't really like units as mathematicians. We just don't want them in the equations, all right? So we can scale things to get rid of the units. And since we're measuring for 180 minutes and the units of K are inverse time, so I'm just multiplying with 180 minutes to make the K unitless. But in your problem, you may want to do something else. So it's like 180 minutes times whatever K is, it's going to be a quantity that has no units. It's still a positive quantity, and we don't really like positive quantities or constraints on the quantities when we solve optimization problems, because if you have constraints, you have to do constraint optimization, which is more difficult than unconstrained optimization. So we get rid of the constraint by changing from positive variables to just real numbers. How do you do that? You just take the logarithm. Is this the only way to do it? No. Is it the easiest? Yes. Okay? So you just take the logarithm of whatever positive quantity you have, and now you have to find an x that is in a Euclidean space, completely unconstrained, and that's nice. Okay? So you should always do that. Do not just try to optimize over the k's, because if you don't worry about the constraints, you're going to start getting negative k's, which doesn't make sense. Okay? Anyway. And we will think of the solution as a function of the x's now instead of the k's, which the x's are just a scaled version of the k's. Okay, step 3, we will have to make the connection between the model predictions and the experimental measurement. So now we have to come up with that f of x that just predicts y. Okay, so this is our measurement. It is basically a table. Okay, it is 5 by 6. I just have thrown the first line, which is the initial condition. I don't need that. I already know what it is. Okay, so I just throw it away. And my model predicts that anyway because it's the initial condition of the model. So this is all the data that I have. 5 times 6. I'll just have it as a matrix for now. And I turn it into a vector. How do I turn it into a vector? Well, just put, let's say, one row after the other, and I flatten it. Okay, that's one way. The other way is to take the columns and put them one after the other. I do the rows here because that's what Python's function flatten does. It puts the rows one after the other, unless you tell it to put the columns one after the other. But by default, it does that. So the correspondence between the model and the data is this. So the first product Z1 at this time step is supposed to predict this. Okay? The second one is supposed to predict that. The third one is that X. It doesn't predict anything. Okay? Because it's not measured. So we skip it. And so on and so forth. Okay? And because it's a little bit complicated, I suggest writing it down, at least the first time that you do it like that. So now I'm going to define that f of x. Yes?
So regarding the unknown chemical,
Yeah.
just take the difference and then call that as the quantity of x, or since you're not actually physically measuring it, is that just not the standard way of doing these kinds of...
So if you want, you could say, but you could say that. And you could add it here, right? But that would not really change anything in the solution you find, because it will automatically match the data if you do it like that. So you don't have, it is redundant. You will find the same answer. But yes, you could do that. But then you're making one more assumption, but we'll come to that later. Okay, so this is the correspondence, and I'm building here a function f whose output is a matrix, which I will vectorize at the end in exactly the same way I vectorized that capital Y. Okay, just to make sure that I don't mess things up. So this is how I construct f of x. Okay. So it's not really the differential equation. It solves the differential equation. It post-processes the differential equation. It just grabs the concentration at different times and just returns me that. Okay?
5 times 6 or 6 times 1.
It is 6 times 5. 1, 2, 3, 4, 5, 6 times 5. Yes. Good eye. All right. Now you program it. Okay, feel free to skip any of these steps and just go directly to programming it. And trust me, it is not going to work. It is not even going to work if you don't skip the steps. It will still not work, okay? The first time you do it, you will still have bugs, but you have less bugs, okay? And you will have, you will be able to isolate perhaps the bugs if you have taken care of the steps, okay? Another important thing of these steps is that if you want to change something, change the model a little bit, you go and you change that A. If you want to change, you have one more additional experimental measurement, you go and you change that F. Right, that's a good thing about writing it down. All right, so now you program it, and this is what we have on the handout, so you're going to be able to see it there. And I haven't programmed the derivative of F with respect to X. And I'm using the square loss, BFGS, and a random initial condition for the optimization. Random initial parameter, let's call it, parameter. So all these optimization algorithms, they start at an initial point, and then they move it around using the information from the derivative. So this is what we find, which seems okay. Okay, but then you decide to do it again, and you get this, which also seems okay, but it is different than the other one. So you can't have both of them being okay. You do it once more, and you find something different, and do it 10 times, you'll find 10 times something different. Okay, so that means that the solution of the optimization problem, the solution that you get, depends on where you start. Okay, and so the loss function, the two possibilities, either the loss function has multiple local minima and you find one of them, or you just have, yes?
Is the solution to the inverse problem unique?
No, not necessarily. No. This is another point I want to make. So there are two possibilities, okay? First, one possibility is that the solution of the inverse problem is not unique, and that corresponds to the loss function not having a single global minimum. Okay, you may have two local minima. Maybe one of them is smaller than the other, but you're not guaranteed to find the smallest one. The other thing is that, maybe the numerical derivatives are wrong. Okay? And in this case, this is exactly what happens. The numerical derivatives are not very accurate. They're accurate at the beginning, but as you get closer and closer to the optimal solution, the accuracy deteriorates. And this is exactly what happens, and I will show you how to fix it. Okay, so yes, you should first try without doing the derivatives, but unless you get something that is spot on, maybe you should think about it a little bit. Okay, so here's what we need to do to get the derivatives. So another thing that we can pass these algorithms is the derivative of the loss function with respect to the parameters that you have. Right, so if you use the chain rule, you will see that you will basically need this derivative, which is easy because you just know your loss functions. The square loss, for example, you can take this derivative, no problem. But you also need this derivative, which is hard because you need to differentiate your model with respect to the parameters. Okay? So you need this matrix, you need the Jacobian matrix. A matrix of all derivatives. And we discussed this in lecture 15, how to get it with the method of adjoints. And let me show you how the method of adjoints looks like for this particular dynamical system. So one of the reasons that I changed the notation is so that I could derive the adjoint system a little bit easier. Okay? So the adjoint system is basically a set of differential equations that tells me the evolution of the derivatives. So these are the derivative of, this is the derivative of z with respect to xj. This is what it is. Okay, the derivative of z with respect to the xj. So it's a differential equation that has to do with the derivative of z, with the time derivative of z with respect to xj, and it's supposed to start at this initial condition. So if you, this is called the adjoint ODE, let's call it, ordinary differential equation, to the original differential equation, and if you solve it, you will get the derivatives. Now let me show you why this is the equation that the derivatives satisfy. It is very simple. It is much simpler than you think. Here's how you do it. You start with what you want. So I want a differential equation for this. The derivative of z with respect to xj. That's what I want. Okay, so let me just take the derivative of this thing. Here you go. Okay, so what is this? This is the time derivative of this. What is this? This is the time derivative of this. Okay, let's write it like this. Now you can swap the derivatives, unless you're too paranoid about it, but you shouldn't be. Okay, so you swap the derivatives. Here you go. It's called the Schwarz theorem, if I'm not mistaken. And then you can take xj out. Xj, okay, and what do you have inside? Well, inside you have z dot. Right, the derivative of z with respect to time, that's what you have. Alright, but z dot, for z dot you can use your original equation, which will give you this. Right, so here I'm using the original equation, right there at this step. And then I just use the product rule there, right? So I'm gonna have to differentiate a with respect to xj times z, and then I have to do a of x, and then the derivative of z with respect to j. That's it. So what did you get? Well, you get this equation. You get that the partial derivative of your response with respect to a parameter of your system should satisfy this differential equation. And what is the initial condition? Well, it's just the derivative of the initial condition with respect to any parameters you have. In this particular case, it's going to be exactly 0, okay? Because the initial conditions do not depend on k, on x. All right? So the method of adjoints, even though it sounds complicated, it is nothing more than just taking the derivative of your response with respect to the parameters and try to use the original equation you have to get an equation for that derivative. That's all. Right, you should really just do it by hand once for whatever you're looking at. We're gonna do it, well, we did it for this dynamical system, very easy. We're gonna do it for, we're gonna have you do it in your homework for the diffusion problem, which is a partial differential equation. And then you're gonna get an adjoint partial differential equation. Anyway, so now that you can program this using the adjoint, if we use the square loss function, this is what we're gonna get, right? For the first part. So this is the derivative of the square loss function with respect to one of the parameters. It would look like that, okay? Now, you may be inclined again to just go ahead and try to optimize, resist this urge, because it will be wrong, okay? So, you should really spend some time comparing what you have just done with a numerical estimation of the derivatives. And I show you in the handout how to do that. Alright, so you can use finite differences to estimate the derivatives, and then you can compare with what your analytical results are. And they should match. I mean, they should not be exactly the same because the numerical derivative is not super accurate. Okay, but they should at least match to some significant digits, like the first one, at the very least. Okay, but do not skip this step, because it is very unlikely that you're gonna get it right the first time, especially when you have a complicated problem. All right. So when we do all that and we solve the inverse problem with the analytical derivatives, this is the solution that we get, which looks much better, okay, than before. It's not perfect because maybe the model is not perfect right now, okay? But it is definitely better than before. So you see that in this particular example, the problem was really with the derivatives. One of the problems was the derivatives. And now if you run this 2 or 3 times, you will still get the same result. Okay? All right. Let's say that you don't want to calculate the derivatives. You really don't want to do it. Because let's say you either have a problem that is way too complicated, or you have a black box problem. Okay? Then the only way around it will be to construct a surrogate of your model and take the derivatives of that, of the surrogate, right? So for example, you can use a polynomial, you can do the following thing. You can simulate your model at, let's say, a bunch of points, xi, and you measure, let's say, yi, and you do that at n different points, and you build an approximation, f hat of x, to your model, okay? For example, using polynomial chaos, or another generalized linear model, or a neural network, or a Gaussian process, okay? But it has to be very accurate in the region of the solution of the inverse problem. Because if it is not accurate, then you will be calibrating this, right? Not your actual model. This is the thing that you have to keep in mind. So even though you can do that, you can use what we have learned in the past, basically in the past lectures, to build this surrogate. And then just go in your inverse problem and replace every occurrence of the actual model with the surrogate. That's all. The surrogate could be a polynomial chaos. If you choose polynomial chaos, then you could use the collocation points for these, right? You could use the collocation points for these. But it could really be anything. Make sense? Alright, so if you can't get the derivatives by hand, don't panic. There is this solution as well. Alright. There are several issues with the classical approach to inverse problems. The problems are ill-posed. It's one of the issues. Meaning that a solution doesn't have to exist. I mean, you will always get a solution. You will always get whatever minimizes the loss function, but this doesn't have to be the truth. Okay, because if your model is wrong, you will get garbage. Make sense? All right. So there's no guaranteed existence of the solution. At least there's 0 of the loss function. There's no guarantee that you're going to get a 0 in the loss function. There's no guarantee for uniqueness. There may be 2 x's that give you pretty much similar predictions, but they're different, and you don't have a way to choose between them. There may be an infinity of x's. There is no way to quantify uncertainties, and you have 2 kinds of uncertainties. One is measurement noise. How do you quantify measurement noise? Different levels of measurement, and the more noise you have, the harder it should be to solve the inverse problem, and so on and so forth. But you also have a different kind of noise, which is model form error, or model discrepancy. Your model may be wrong, the model is wrong, okay? So the question is, it could be wrong in many different ways. Is there any way you can quantify this model error, the systematic model error? And the other problem is that, well, you may know a lot about the parameters already, or you may have prior beliefs about them. Like, for example, this x cannot really be a billion. I know that it should be around 10. How do I know? Well, I know, okay, it's physics. It cannot be whatever. If it is a mass, it has to be less than the mass of the Earth, right? It's a crude estimate. Or greater than, than the mass of an electron. So you always know things. And the classical approach doesn't give you a lot of ways. It gives you only one way to incorporate this prior knowledge, and this is through the constraints that you put in the optimization problem. But if you have more complicated beliefs about the parameters, you cannot really do anything. So for example, yeah, let's just leave it there, okay? Let's just leave it there. All right, so we have 8 minutes left for the handout. This is probably not enough, but at least you can get it started, or you can start talking about the homework, the new homework problems that I do next week. But there's no class on Thursday because I have to go to an NSF workshop. Okay, so just keep that in mind. And so the homework is due next Thursday? Tuesday, okay. So no class on Thursday, but the homework is due Tuesday. You can get it started now. And it's going to be on polynomial chaos. It's not very hard, but it's not really very easy. It's right in the middle. Okay. One more thing that I want to say. So we haven't talked about the project at all after your submission of the abstracts. Okay. But hopefully by now, I mean, when you submitted the abstracts, you didn't really know anything about uncertain quantification. Otherwise, why would you take the course? So, you know, understandably, there's a lot of details missing, like what kind of methodology we're going to use, what kind of problems we're going to solve. So, I realize that I think you learn more from homework than you do from obviously the lecture or a project that is a little bit vague. So here's what we're gonna do. We're gonna give you more homework than we have in the syllabus, a little bit more, like 1 or 2 more homework. And the project is basically going to be a write-up of the approach you would follow for your problem. So you would go back to your abstract and you would say, okay, now I can see that my problem is an inverse problem. I can see that my problem is an uncertainty propagation problem. And I have the following issues. I have an expensive solver, therefore I would have to replace it with a surrogate. And I would use the polynomial chaos surrogate. So you would describe that and you will be graded. You will be graded on describing how you would do it, okay? And if you have time, of course, you can do it. But now, realistically speaking, this is not going to be the case for most of you, okay? So you're not going to be graded on how successful you are. You're going to be graded on your ability to write down the steps you would follow. And we will grade that and we will give you, hints of what is the best way to approach your problem. So that would also be useful. If the problem is from your research, it will be also useful for continuing your research. Okay? So don't get too stressed about the project because it will be, the amount of effort you will have to put on it will be equivalent to 1 or 2 homeworks. This is the amount of effort you will have to put on it. Okay, and I will give you guidelines later. All right. Okay. Next time we do the right way. We are going to talk about the right way for solving inverse problems, which is the Bayesian way. And then we're going to start Markov chain Monte Carlo. And the reason we start Markov chain Monte Carlo is so that we can actually follow the Bayesian approach to the end for inverse problems. All right?